Can a triangle have an area even when the triangle itself cannot exist? It sounds impossible, and that's exactly what makes this problem so interesting. We're given three side lengths, 1, 22, and 27, and we're asked to find the exact area. At first, this looks like a straightforward Heron's formula problem, but there's a catch. Let's check whether these three lengths can actually form a triangle. The triangle inequality theorem tells us that the sum of any two sides of a triangle must be strictly greater than the third side. So take the two smaller sides. 1 plus 22 equals 23. But 23 is not greater than 27. It's smaller. So these three lengths cannot form a real triangle. The triangle is impossible. But now comes the strange part. What happens if we ignore that fact and simply substitute the three numbers into Heron's formula? Let's see where the mathematics takes us. First, we need the semi-perimeter. Let's call it S. S equals 1 plus 22 plus 27, all divided by 2. The total is 50, so S equals 25.
Now, Heron's formula tells us that the area equals the square root of S multiplied by S minus A multiplied by S minus B multiplied by S minus C. Let's substitute our values. The area equals the square root of 25 times the quantity 25 minus 1 times the quantity 25 minus 22 times the quantity 25 minus 27. Now simplify each bracket. 25 minus 1 is 24, 25 minus 22 is 3, and 25 minus 27 is negative 2. So the area becomes the square root of 25 times 24 times 3 times negative 2. And this is where things get interesting. 25 times 24 is 600. 600 times 3 is 1,800. And 1,800 times negative 2 is negative 3,600. So our formula gives us the square root of negative 3,600. That's not a real number. And that makes perfect sense because the triangle itself isn't real.
But mathematics has a way of extending beyond the real numbers. Using the imaginary unit I, the square root of negative 3,600 can be written as the square root of 3,600 times I. And the square root of 3,600 is 60. So the result is 60I, an imaginary value. And that's the fascinating part. A triangle that cannot exist in ordinary geometry produces an imaginary value when we force its side lengths into the formula. So the real lesson isn't that an impossible triangle has a physical area of 60I. It's that the algebra is revealing exactly where the geometry breaks down. Sometimes a strange answer isn't a mistake, it's a clue.